Okay, so since we've covered kinematics, we've looked at how things move. So in terms of what happens to velocity, what happens to acceleration, but we haven't talked about why things move. So this particular section, we're going to look at forces, and forces are the reason for why things move. So specifically, we're going to start with Newton's law. So this is a nice introductory section. We're going to definitely get into some more vector stuff with this section. And you won't use as much of the kinematics that you last used, other than you're going to use acceleration a lot. But those big five equations, you might see one or two of them pop up periodically, but it won't be as much as you had before. I would argue the math gets simpler from here on out, and in my opinion, but that's just from my perspective. You may disagree with that. So forces. A force is any push or pull. It's directly proportional to the mass of an object. So the heavier an object is, the more force it takes to push it or to pull it. And that's pretty intuitive to us. All you have to do is imagine you're on the ice playing hockey. There's a reason why usually the checking's done by the big guy, not the little guy. All right, so force is directly proportional to mass. The unit for force is Newton, and it's named after John Newton, who really discovered the three laws that we're going to look at. And a Newton is equal to a kilogram times a meter per second squared. So it's always kilograms would be mass, meters per second squared is acceleration. So we're going to find that force is equal to mass times acceleration. Now, mass is the amount of matter an object is made up of. So it's how much stuff makes you up, but it's not your weight. Weight changes depending on where I am in the universe. If I'm on the moon, my weight changes, but the amount of stuff that makes me up does not change. And that's just because gravity is involved in weight, and it changes depending on how far apart your bodies are. So mass is constant throughout the universe. So anytime we're talking about mass, we're always going to be thinking about kilograms. When I ask you questions about weight, we're going to find that I'm going to be including gravity. And we'll see that a little bit as we go. I've said up front, mass is not equal to weight, because I'm hoping when I say that again, it will actually stick for you. So Newton's first law is an object in motion will stay in motion, and an object at rest will stay at rest unless acted on by an external force. So we've got this lovely little GIF here. We've got the little guy riding his bike into a wall. The bike stops because the wall exerts a force on the bike to stop it. But the body of the little guy keeps going because his body is in motion. And Newton's first law says it will want to stay in motion unless acted on by another force. And because obviously there's no seatbelt here, he's going to keep going. It's also the reason why we have things like seatbelts and airbags in cars, is because otherwise, in the event of a collision, bodies would fly out of cars, which is definitely not good if you're a paramedic of any kind. Let alone passenger or driver, we'll put it that way. So Newton's first law is also known as the law of inertia. So inertia is just the property of matter that resists change in motion. Okay, so inertia is kind of one of those weird things, and it's hard to describe. Because of inertia, an object wants to maintain whatever motion it has. So let's say I'm in a spinny office chair right now. So let's say I push myself back and lift my feet off. That chair is going to want to keep going until it hits something else, assuming there's not a lot of friction in the wheels. This chair is a new chair, so right now there's not much friction with those wheels. So that's going to be the law of inertia. Technically, the heavier I am, the more push it's going to want to stay in the motion that it has. So the heavier I am, the bigger a push it's going to take me to move, because my body will want to stay at rest. Likewise, if my body is moving, the law of inertia says that if my body is moving, if it has a big mass, it's going to take a lot of force to stop it, because my body will have a lot of inertia. So you can think of force and inertia as being similar, but inertia, if you want to think of inertia, is how much force we're going to need to get something moving or to stop its motion. Okay, I think there's a great little video that uses hockey as an example, and I'll post that for you should you need to see some visuals. But I think if you think of it as you watch a hockey game, and visualize Newton's laws, and it could help you a little bit with some of the questions and concepts. All right, so inertia is directly proportional to mass, which means the more mass something has, the more inertia it has, or the more mass something has, the harder it is to change its motion. All right, so Newton's first law in math speak, of course, we're going to relate everything back to math. So in math speak, Newton's first law says that if an object has no force on it, it's going to keep its motion or it's going to be at rest. So by keeping its motion, it's going to have, and the key word here is it's going to have a constant velocity, or it will be at rest. Those are the two possible scenarios. That's the net force being zero, so there's no overall force acting on it. There may be forces, but added together, they add up to zero. So let's imagine the example we have here. We have a book sitting on a table. There's a force of gravity pulling it down. We know there's gravity pulling that book down, but it's not moving. Newton's first law says if it's not moving, it must have a balancing force pushing up. We actually call this the normal force. The reason we call it normal force, normal means perpendicular, so it's perpendicular to the surface. And this would be our force of gravity. So the book does not accelerate, it just keeps its motion because it's on a table, it's supported, the forces are balanced. Okay? You could have a car driving down the road. If you have balanced forces between the friction between the road and the wheels and the engine, the car will go at a constant velocity. If those forces aren't balanced, you'll speed up or you'll slow down. So Newton's first law in action. So these are a couple examples. This first one, usually there's 2 or 3 people in the class that have done this before. If you haven't, it's a good one to try. If you find something that's got a loose hammer head on it. The head of a hammer can be tightened onto a wooden handle, any particular handle, by banging the bottom of the handle against a hard surface. So you take your hammer and you smash it down on a hard surface. The handle stops, but the head is in motion and it keeps moving until it's tight enough it can't move anymore. So that's Newton's first law. The head of the hammer wants to keep moving because it has inertia. Make sense? So if we were to sketch it, we've got our handle. This is where I kind of wish I like using hand gestures better because my artwork isn't very good. So you bang the hammer onto a table and this head keeps going down and tightens up. I remember doing that numerous times in my dad's shop. I didn't know about the law of inertia when I used to do that, but that was one of the things that we used to do. The other thing we used to do with a wooden hammer is when it got loose, we'd soak it in water, and by soaking in water, it would swallow the wood and the hammerhead would get tight because wood dries out. So we don't see wooden hammers very often anymore, but that was how we used to deal with it. Next one says, while sitting in the back seat of a car, it makes a hard right turn and you slide across the seat. Okay, well, let's use Newton's law of inertia. So you're driving down the road in the car. Okay, so you're driving in the car. We'll draw a little box to be our car. The car makes a hard right turn. The car goes this way. So if you're in the car there, and you're driving down the road, or you're, whatever, you're wherever in the car. If you're in the back seat, I guess you're not driving. If the car turns right, you want to keep moving forward, which means when the car is on the corner, your body, instead of turning with the car, wants to stay where it is. It wants to stay in a straight path. So you're going to land in another part of the car. You're going to end up that sliding feeling you get across leather seats. That's what my poor diagram is trying to draw. It's not doing very well, but that's Newton's law. Your body wants to keep going with the initial motion of the car, and unless there's enough friction between you and the seat, you're going to slide and the car will move till there's enough force on your body to bring you back in line with the car. I'm pretty sure most of you have probably played with something like that before. All right, Newton's second. So that's Newton's first law. Newton's first law is just An object in motion stays in motion, an object at rest stays at rest. So if there's a puck on the ice, if it's moving, it's going to keep moving until it hits something. We've seen that before. If it's at rest, it's going to stay at rest until somebody hits it. Imagine if it didn't. It would screw the game of hockey up pretty good. All right, so Newton's second law. An unbalanced force results in acceleration. Well, let's think about it. You have an object at rest. For an object to go from rest to a speed, we know there has to be acceleration. You did that in your last section. So that tells me that if I apply a force in order to get an object moving, I must be causing an acceleration to occur. So that's Newton's second law. He says the net force, the overall forces on an object, we add them all up, it's equal to the mass of the object times the acceleration of the object. Okay, so let's think of this scenario. Instead of a book on a table, this time we have a book that's fallen off a shelf. There's only the downward force of gravity on it. We're going to take out air resistance. Well, what force is acting on the book? The book accelerates towards the ground because it has a force, one force on it, the force due to gravity or the net force, and it's equal to the mass of the book, so how heavy the book is, times the acceleration of gravity, which is 9.81. Now, oftentimes when we're doing forces, we'll just put, instead of putting the negative sign with 9.81, we'll use arrows in our diagram. So you'll find that I'll often leave the negative out and we'll use the diagram to support and add that in. So that's just something helpful along the way. So because we have this downward force, the book accelerates towards the ground. Well, whoops, you've looked at that in the last lesson. In the last lesson, we looked at, well, if it's accelerating, how fast does it hit the ground? Now that we know how to use net forces, we could technically put air resistance in and find out by how much does the acceleration change. We're going to hold off on that for just a little bit. All right, so let's do a couple of calculations using Newton's second law. So Newton's second law says that force equals mass times acceleration. A 5 kilogram block is pushed to the right along a frictionless track with a force of 10 newtons. What is its acceleration? So to figure this question out, we know that we have a force. It's a frictionless track, so that means there's no other forces on the object. I'm going to draw a free body diagram, even though I'm going to kind of detail what a free body diagram is in a little bit. So we have, let's see, not sure what happened there. There we go. So we have a block. It's being pushed along a track with 10 newtons of force. And there's no friction. There's nothing in the other direction. We know there'd be gravity on it, but we really don't have to worry about that because gravity is pulling it down, but we're also going to have the track holding it up. So it's not going to be accelerating up and down. So it's being pushed to the right. What's the acceleration? So the net force is equal to the mass of the block times the acceleration. So net force is equal to 10 newtons. That's equal to 5 kgs times the acceleration. Divide both sides by 5 kg. And our acceleration is equal to 10 divided by 5, leaves us 2.0. I'm going to leave my erase here just to give myself enough space to put the units in. You guys know the units for acceleration at this point. 2.0 meters per second squared. So nice, easy question. Of course, this would be a great time to ask you to find its final velocity, but we're going to leave that out. That's going to add way too much time to our questions. You may see that come up later. Just saying. The next one, a 650 kg car accelerates at 3 meters per second squared south. What's the net force acting on it? So we have our car. I'm going to just draw it like a box, keeps it easy. You could draw a dot if you want. We know it's accelerating south. So it has a force, a net force, or the sum of the forces add up towards the south direction. We want to know, well, how much is the net force? Well, the net force is equal to mass times acceleration. Nice, easy math. So it's just 650 kgs times 3 meters per second squared. Should throw my squared up here. And that gives us 1,950 newtons of force. If you want to do sig figs would give me 2,000 newtons is what we'd have to round to. And to show that we have two sig figs, you put a little line on top of the second zero. It shows me that I keep that. Okay? So like I said, the math is way easier in this section than it was in the last one. You've done the hardest math already. All right, the next one. Stan and Kyle are pushing a 750 kilogram box along the frictionless surface. Stan pushes with 55 newtons and Kyle pushes in the same direction with 45 newtons. What's the acceleration? So sometimes we have more than one force. So there's our box. We have one pushing there. We get another pushing. So I have 55 newtons and 45 newtons. Sorry, I probably should have. Let's see, I can do a little adjustment here. I don't like the fact that the arrows don't line up with the sizes. There, I like to have them approximately equal to the sizes that we could have. All right, so 55 newtons and 45 newtons, the net force is equal to 55 plus 45. That gives us a total of 100 newtons. Okay, the acceleration, well, F net equals mass times acceleration. So we know we have 100 newtons of force. That's equal to 75 kgs times acceleration. Divide both sides by 75. And acceleration is equal to 1.7 meters per second squared. Right? So pretty straightforward. For the next one, we have a vehicle with an engine that exerts a force of 8.5 times 10 to the power of 3 newtons. So I told you the scientific notation would show up. We'll see how we write that. While friction pulls back with a force of 1,500 newtons. If it has a mass of 1,250 kg, what's its acceleration? So this number, 10 to the power of 3 means take the decimal and move it 3 places this way. So 8,500 newtons. So if you're wondering about how to change that, the 3 means I move 3 decimal places towards the right. So we have our car, and the engine is pushing it forward with 8,500 newtons. But we know friction is going the other way, 1,500 newtons. What's the net force? So the net force is equal to, we're going to subtract the 2. We get 7,000 newtons. So now if I want to calculate the acceleration, F net is also equal to mass times acceleration. So we substitute our 7,000 in. That's equal to 1,250 kgs times the acceleration. Divide both sides by 1,250. And acceleration is equal to 5.6 meters per second squared. Now there's a little note here at the bottom and it says always draw a diagram to identify which forces act together and which work against each other. We'll practice a little bit of free body diagramming, which is these little diagrams that I've done here. They help solving problems with forces tremendously. I'm always drawing boxes and arrows. It's going to make a big difference for you. So do take the time to actually write them. A question like this, I could argue you could probably get away without it, but it really will help you visualize, especially it'll help you eliminate things like you won't miss negatives. Okay, so you'll see the opposite directions. It's going to be really, really important as we add more complex forces in. So get in the habit of drawing those little box diagrams, but we will, by the end of this lesson, we'll have done a few more. Now, gravity is an example of Newton's second law. We know acceleration due to gravity is negative 9.81 meters per second squared on Earth. It's going to change depending on where we are in the universe. So the formula for gravity is the force due to gravity is equal to mass times gravity. Acceleration due to gravity. So it's just an application of Newton's second law. All right. Now, weight depends on gravity. So the force of gravity is equal to weight. It's one of those technical things in physics. We have mass and we have weight. It's kind of like saying speed and velocity. There's a technical difference. So weight is a force. Weight is the force due to gravity. Now your scale, if you're getting on a scale, it's calibrated for Earth. If you took that same scale and you stood on it on the moon, it would not give you an accurate weight on the moon because it's calibrated for Earth. So that scale has been calibrated in such a way that whether it's electronic or if it's like an old spring scale, that the spring is calibrated so that for every kilogram, it basically, I was going to say, it divides out that 9.81 just to give us what our mass happens to be. Okay, so it's one of those things that we kind of have to keep an eye on. And it's one of those kind of weird concepts because we talk about our weight being kilograms, but weight is in physics is actually the force due to gravity. Okay, so just one of those technical things to keep in mind. Now Newton's third law, it's the last one. For every action, there is an equal in magnitude and opposite in direction reaction force. So the easiest way to describe this one is, well, if I'm sitting in a chair, I am not accelerating. If I was accelerating, you would either see me levitating up past the screen, or you would see me plummeting down through the floor, but I'm not. I may be moving horizontally, but vertically I'm not moving. I'm pushing down, definitely pushing down on the seat of the chair. So what's holding me up? There has to be a force balancing gravity. And that's what we call that a normal force, but Newton calls that one of the reaction forces. A normal force we'll learn is a reaction force. It's the force that holds you up. Sometimes we'll call it elastic recoil of a floor or of a surface, and it's how much that surface can hold you up. If you're on a springy board, the board may deflect a little bit. That's because it can't quite support the force, and then eventually, as you put less weight on it, it comes back up. That's an example of normal force at work. So normal force springing back up. So that's Newton's third law. If we let's take a look at these two vehicles here. We have a big truck and a small truck collide. Now, any of you that have been on an accident scene, you guys know what happens when a big truck and a little truck collide. In particular, maybe in this scenario, it's not quite as dangerous, but in particular, if you've got a large transport truck and a small car. I've been behind one of those and it's not pretty. So what are the reaction forces? Well, the large truck pushes on the small truck with exactly the same force as the small truck pushes on the large truck. The forces are equal and opposite. But what causes the chaos is the fact that their acceleration is different. Okay? So the force pairs, we've got big truck on little truck and we've got little truck on big truck. Which one's bigger? They're both the same. The forces are equal, but their accelerations are not. The large truck does not slow down at the same speed as the little truck. We know that. The little truck slows down much faster, which is why oftentimes the little truck slows and then it keeps moving with the big truck. Because the force isn't enough to compensate for all of the force, the extra force from the engine that's still being applied of the large truck. Okay, so the inertia of the big truck keeps it moving. That's Newton's first law. The large truck doesn't slow down as quickly because it has a larger mass. That's Newton's second law. And Newton's third law says the forces with which they hit at the moment of impact are equal. Sometimes it's easier to visualize that in a stationary scenario. If I lean against the wall, I'm pushing against the wall. Is there a reaction force? Yes. The wall pushes back on me. Otherwise, I would go through that wall. You put a piece of paper on your desk. That piece of paper doesn't go through your desk. There's a reaction force the desk pushes up on the paper. Those forces are always equal and opposite. The point at which your force that you're pushing on, when the force you're pushing on a desk with, when it becomes greater than the force that the desk can push back on you with, the desk will collapse and you'll have a hole through the desk or a hole through the wall, whichever it happens to be. Okay, so those are Newton's 3 laws. First law, law of inertia, an object that's moving wants to stay moving. That's why checking works so well in hockey. That's why it hurts to hit the boards. Okay, an object at rest stays at rest. Well, that's also a good thing. We don't want to constantly be moving. We have to apply force to get that motion to start. Newton's second law says that the more mass I have, the more force it will take to accelerate me. Well, that makes sense. I got to push harder to move. Or if you want to think of it in hockey, if you want to push the little guy out of the way, you're going to send the big guy to give him a push. And then Newton's third law says that for every action, there's an equal in magnitude, opposite in direction reaction force. So since we're using hockey as examples, and I'm not a hockey person at all, so bear with me if I don't use all the right terms. But if you check somebody, you put force on them, they put force back on you, okay? And those forces should be considered equal, often equal and opposite forces. If they push back on you with a larger force, technically they could cause you to move or you could cause them to move, all right? But this would be like for a reaction where we have a collision and stops, okay? My hands are pushing on each other. Even though maybe I try to push harder with this hand, in order to keep the other one from moving, I have to push back equally or else my hands are going to move. All right, so let's summarize some of the forces you're going to see. I think those rules are pretty straightforward. They explain a lot of things that happen around us. We use them every day, we just don't think about them. All right, so some of the forces you're going to see, this chart could be a good chart to might be a good chart to print off and keep handy if you're afraid you're gonna forget what terms are or what letters happen to be. So the gravitational force, I always use the Fg in order to represent it when I'm labeling it in a diagram, and it's equal to mass times the acceleration due to gravity. And we can assume that gravity is always 9.81 for our purposes. You will be told if it's something else. Or if you're asked to calculate it, you could assume you might be somewhere else. Force of friction, FF, force, little f for friction. We're going to look at this equation later. You don't need to worry about this equation right now. We will talk about the normal force, which is F with could be big N or little n. I usually use a little n. I always just put n with it though. And it's the balancing force that opposes gravity. So it's what pushes up from any surface, and it's always perpendicular to a surface. So normal actually means at 90 degrees. So it's perpendicular to a surface. So if you have something sitting on a table, you're going to have gravity down, and the normal force often will be equal and opposite, sometimes not, but our normal force opposes that, it balances it out. It's that reaction force from Newton's third law. Applied force, it could be anything that's a push, an engine thrust, a person pulling or pushing, and applied. Often questions will talk about an applied force being added. And the net force is just the sum of the forces on an object. You can either add all the forces up, or you can use the equation force equals mass times acceleration from Newton's second law in order to figure out what is the net force. So sometimes you'll have to use both of those equations. So knowing both of them is going to be important for you. So this is a great little chart to keep handy. We'll be referring back to the pieces in here quite often. Now I want to take just a minute and talk about some free body diagrams. Now I've listed several forces here. I've broken a couple of them up just because, and there's a worksheet that goes with this that uses the same forces, and it'll let you kind of think about what forces you would use. We're not going to use all of these. So we've got force of gravity, force applied, force of friction, normal force. F air, force of air resistance. It's just a way of labeling that I know where this force is coming from. We won't use that in one of these examples, but now if we have something falling through the air, we can think about air resistance. We can figure, well, how much force does air resistance apply? And then T will often tension, that's just force acting in a rope. So those are some examples that we can have. You can use other labels for them if you want, but these are the most commonly used ones. So a free body diagram is just a simple diagram that shows all the forces acting on an object, and it's often critical to solving problems. So we'll do a couple examples here. We'll start with the first one. A box is pushed across a rough floor at a constant velocity. So I want to draw the free body diagram for this. So there's my box. It's across a rough floor, so there's friction, but it's being pushed. So I tend to draw my arrows out from this, pointing out from the box. So I know it's being pushed, so there's a force applied. Constant velocity, we had that back earlier. Newton's first law says if there's a constant velocity, F net equals 0. So that means if the net forces are 0, the applied force should be equal to the force in the other direction, which would be the force of friction. Friction is always opposite the motion. So the forces are equal. So force of friction is equal to the force applied. Pretty straightforward. A crate is being hoisted into the air by a crane at a constant velocity. So again, we have equal forces. If you don't have constant velocity, if it's accelerating, the overall forces have to be in the same direction as this acceleration. We'll see one or two of those as well. So we've got a crate being hoisted into the air. So we have a rope that's holding it up. That would have tension in it. So force from tension. You could also call applied force. Force from the crane, whichever. We also have the force due to gravity, pulling it down. And we know that, I'll call it tension, is equal to the force of gravity because constant velocity F net equals 0. So those are simple free body diagrams. It's just a way of visualizing, and I'll often try to make the arrows roughly, if a force is smaller, I'll make the arrow smaller so that at a glance, I can go, oh, I think this is the direction of force. Now you can probably predict that you're going to see some two-dimensional forces coming up in the near future. All right, so just to do some really quick calculations, and these are very easy calculations. You get off easy this week. Use the free body diagram shown to calculate the net force acting on the object and describe the motion if there is any. So I'm going to just kind of section these charts off into 3 areas. So for the very first question, so we have 4 forces acting on this box. 5 newtons of friction, 5 newtons applied. In the horizontal direction, the forces cancel out. So there's no horizontal force. So let's look vertically. Force due to gravity is 3 down. Normal force is 3 up. They cancel out as well. So this tells me my net force is equal to 0. Now, what kind of motion does it have if there's no net force? Well, friction only happens when objects are moving. I shouldn't say only, it's usually when objects are moving. You can have friction if there's a stationary object, it is true. Usually, we would consider friction with an object moving. So if this was a moving object, we know it has constant acceleration. Constant acceleration, wrong word. Constant velocity. Hopefully you got that. So it has constant velocity, it's moving at this constant speed. Or it's not moving at all. I mean, technically, if you just think about a car, friction between your tires and the car keeps your car from rolling down a hill. But you know you have to apply gas, and there's a point at which you've applied gas, you apply, and all of a sudden the car starts rolling upwards. The engine is applying more force than the force of friction. Okay, or the force due to gravity. So, I mean, technically we could say here that the force of friction occurs when something is stopped too. Okay, you could also think about I have a heavy piano. I'm hoping to get a couple fellas to move for me, and I can push on that piano and I can apply a force, but the piano doesn't move because the friction between the piano and the floor is too great for the object to move. So in theory, up until the applied force is bigger than friction, the object's not going to move. If it is moving, this would be at a constant velocity. We'll look at the details on that in a little bit if that sounds confusing. Situation B, which way is it moving? So we've got a normal force up, gravity down, they balance out. So we know it's not going anywhere horizontally. And the other thing is, if there's a normal force, it has to be on a flat surface. We also have friction, but we don't have an applied force. So we have a net force is 5 newtons and it's left. This is our net force. Okay? We know it's accelerating left because the net force is towards the left. Situation C, we've got vertical balanced forces. So again, F net equals 0. And I would predict this object, because there's no applied force or anything, I would predict that this is not moving. Let's say it's at rest. Okay? It could also be at a constant velocity. You could argue constant velocity. We'll put that in just to cover all the bases. And then for the very last one, we have air resistance, 40 newtons up, gravity, 20 newtons down. Okay, so this object, we know it's something that's falling. Okay, the F net is equal to 40, take away 25, leaves us with 15 newtons up. Now it's accelerating upwards, which means the object is slowing down, which is the whole reason why we do parachutes, is because that increases the force due to air resistance and it slows the descent. Okay, so we get deceleration when the direction of motion and acceleration are opposite, something is slowing. All right. And one last question. Use the free body diagram to calculate the unknown forces and assume all forces, all downward forces are Fg, and find the mass of each object where it's possible. All right, so in order to figure this out, first one, we have net force equals 0. Net force equals 0 tells me my forces are balanced, which means my upwards force has to be 200 newtons and my leftward force has to be 50 newtons. They have to balance. If I want to know the Fg, I could say Fg equals mass times gravity. I've got 200 newtons is equal to mass times 9.81. And we get a mass equal to 20 kg. Okay, so we're just using this as equal to Fg. We know here, if this is Fg, our mass is still going to be let me get my eraser here. We know our mass is still going to be 20 kg because we have the same force of gravity. Now for this question, this example, we have 20 newtons down and it says F net is 900 newtons up. So we know our overall force has to be the upwards direction. So C should be larger than the downward force. So F net is equal to force, these two forces subtracted from each other. So I'm going to say C is the larger one. So it's going to be C minus Fg because it has to be force overall upwards. So 900 is equal to C minus 200. We can rearrange that easy. And we get 1100 newtons equals C. So when the forces are in opposite directions, you end up subtracting them in order to find what your net force is. You'll notice 200 was a downward force and we subtracted it. It's another way you can think of using your signs to help you. All right, let's look at the next one. F net is 60 newtons left. Okay, so what's the rightward force? So we know that 60 newtons has to be equal to, well, if it's moving left, it's going to be 80 minus D, because I want to have my left side as the larger side. So if I want to rearrange it, let's subtract 80 from both sides, and we get 60 minus 80 gives me negative 20. Equals negative D. So 20 newtons is equal to D. Okay, so subtracting the two, we get 60 newtons. And that makes sense. All right, oops, that should be a 20. What I did here was by subtracting 80, I get left with negative D, so I flipped the signs. Okay, if you have negative on this side and negative on this side, it's the same as dividing both by -1. We could have also written this as 60 equals D minus D minus 80. I think that would have worked for us to give us the same result. Think about that one for a second. All right. So just figure out the balancing force. Now we know up and down, there's no motion because the net force was left. So this has to be equal to 300 newtons. And if you calculate the force of the force due to gravity, if we say this is the force due to gravity, then you'll get a mass equal to 30 kgs. And that's just because the force of gravity is approximately 10. And for the very last one, F net is 30 newtons, right? So I know 30 newtons is equal to, there's more force on the right, so G minus 20 newtons. So that's the largest side. And we're going to add 20 to both sides. So 30 and 20 gives me 50 newtons is equal to G. All right. And then up and down, we don't know a whole lot. We can't calculate the forces, but we know if it's only moving right, the force up, force F has to be equal to force H. So the net vertical equals 0. All right, so they're really pretty straightforward calculations, other than once in a while when I have a mind blank on easy number math. Straightforward calculations. There's a couple worksheets to do with them and just a quick quiz and exam. So I'll let you give those a try and see where you get.